Okay, so now the second lecture is microwave remote sensing systems. So if you see this microwave remote sensing systems, they are also working in both the domains, means in the active as well as the passive domains. So as we understand in the passive sensing, we are using the sun as an energy source. So if we are using the sun energy as a source of this remote sensing, then and we are using the microwave sensor, then it is called the microwave passive sensor. Okay, but it is not directly working like radiation is coming from the sun and then reflected from the earth surface and again moving towards the sensor. It is not working like this, but this passive means it is working on the emitted signal from the earth surface. Emitted means if radiation is coming from sun, so part of it is reflected, but system is not catching the reflected energy, but apart from the reflected, some energy is absorbed by the earth surface. So whatever is absorbed, later on it is emitting the radiation. So whatever the radiation is emitted, in that radiation so many wavelengths are there, means that maybe in the optical range, maybe in the infrared, maybe in the thermal range, and maybe in the microwave range. So whatever the emitted signal is there, so this is also a packet of different wavelengths. So in that packet, some microwave radiation is also there. So that in proportion it is very less, but whatever is, so that emitted signal in the microwave portion is moving towards the sensor side, aperture way or the synthetic aperture way. Also that we can say the synthetic aperture radiometers and the real aperture radiometers. So that is called RAR, real aperture radiometer, and SAR, synthetic aperture radiometers. And then some sounders are also there, so which are basically are used for investigating the different layers of the atmosphere. So from different layers the signal is getting reflected, so that energy is basically stored or the catch by the sounders and reflected in the form of the remote sensing products. So this is one way of investigation of the microwave signals, or you can say microwave emitted signals from the earth surface or the different layers of the atmosphere. In different layers of atmosphere in case of sounders, and from the earth surface in case of the radiometers. And these are very popular devices, and nowadays people are using radiometer data very frequently. So you might be aware about the SMAP, that is called the soil moisture active passive. Recently, I think in 2015 NASA basically launched SMAP mission. So, and the specific science objective was to monitor the soil moisture, global soil moisture, using the active as well as the passive devices. So they are using the radiometers as well as the active remote sensing images, or you can say the radars. Both of them they are using, and they are investigating the soil moistures at different resolutions, 9 kilometer resolution or 36 kilometer resolution. So why they are using both active as well as the passive? Because some advantages are there with the passive devices and some advantages are there with the active devices. So the and both of them have their capabilities also. Like the radiometers data is very sensitive with respect to the soil moisture. It means they don't want to lose the sensitivity or high sensitivity information of the radiometers for the soil moisture retrieval. So you can say whatever the radiometers are investigating the soil moisture, so that is very sensitive information. But problem is the resolution is coarse, because as we mentioned, no, they are working on the emitted radiation. So, and in emitted radiation itself, only microwave emitted radiation. It means very few signals are there, or very small energy is emitted from the earth surface. So that energy is not reaching, from a small area, it is not reaching towards the sensor side. So what is happening? We are combining the emitted signal over the large area, and that combined signal we are observing. So that what is happening? The pixel size in the passive remote sensing sensors is increasing very large. Or you can say the pixel size is very large, or you can say spatial resolution is very, very low. So you can say if its resolution is very low, then it is not making sense. Sense means if you see the soil moisture, so soil moisture is changing very rapidly, especially in the Indian context. If you see, the agricultural fields are very, very small in nature. But if you are calculating the soil moisture at 9 kilometer by 9 kilometer pixel, it means it is very big pixel. It is combining so many fields. So by combining so many fields, we are only giving no soil moisture, only single value of the soil moisture. So that way you can say if 9 kilometer by 9 kilometer pixel or single value of soil moisture we are getting, it means we are not able to satisfy, or you can say we are not satisfied about such types of the investigations. Okay, so you can say the spatial resolution is very, very coarse from these passive devices. So that is basically the disadvantage. But the advantage is these radiometers are very sensitive for the surface emissivity. So emissivity, if you are multiplying the emissivity of the surface with the temperature of the surface, so you can say emissivity is E into T is the temperature, then it is basically giving the brightness temperature of the surface. So the brightness temperature can be directly linked with the soil moisture. So that way it is very, very sensitive, or you can say direct relationship with the soil moisture. So you can say in principle it is very sensitive, but drawback is the pixel size is very big. So can we use any other type of the data set which is basically having a small pixel size, so that at the field scale we can investigate the soil moisture? So answer is yes, because then we can go to the another devices, let us say active devices. So active sensors, you can say, so active sensors have their own source of energy, means they generate the microwave energy themselves, and that energy they transmit, and after interacting with the target, the radiation is coming back, or backscatter signal is reaching to the sensor again, and that signal they are basically converting into in the form of the images, and those images are basically the amplitude images and the phase images. So for this active microwave remote sensing, we are using the radar systems. Radar is radio detection and ranging. Radar stands for radio detection and ranging. Detection and ranging means they are basically detecting, as well as ranging means finding the distance between the sensor and the target. So suppose we are sending some signals, signal is moving towards the target, and when it is reaching to the target, it is interacting and then again coming back to the sensor. So it can tell you how much distance is there between the sensor and the target. So they are basically able to monitor the distance. That's why that is basically called the ranging. Detection means once it is coming back means it is interacting or hitting the target. Since it is hitting, it means it is detecting the target. So both the things it is doing simultaneously, means detection as well as the ranging. So if suppose you want to monitor some aircraft, so again and again signals are going and coming back, it means they are able to monitor how far that aircraft is and in which direction it is moving. So the range and the detection part can be done very easily using the radar devices, and they are working mostly in the microwave portion. In radio waves they are also working, but here we are basically more concerned with the radars working in the microwave portion of the electromagnetic spectra. Then again, these radars are of two types. One is imaging radar, another one is the non-imaging radar. Non-imaging radar means they are not forming the images. They are just giving, the attribute information, or you can say the signal is going to a particular target, and whatever the backscatter energy is there, that they are storing in the form of the in the files, or the, you can say the satellite data. but they are not forming the images. But in the imaging radars, they are basically scanning the entire region and converting in the form of the images. So those in that case, we are getting the images. So based on this concept, they are classified as a imaging radar and the non-imaging radar. So in imaging radar, again, there are two types of the things. One is called the real aperture radar, RAR, and another one is called the synthetic aperture radar, that is SAR. Real aperture radar means if uh, that is directly related to the antenna length of the radar. If the actual or the real antenna length we are using for acquiring or acquisition of the images, then it is called the real aperture radar images. Okay, but this spatial resolution is related to the antenna length also. So point is, if more antenna length is there, it means we can get high resolution images. But very large antenna we cannot create with the satellite itself, because very large antenna is not possible. It means practically we cannot increase that antenna length very long. It means we cannot get very high resolution images. So for that, what happens, if we are basically searching a techniques by which we can increase the antenna length. So that way is basically called the enhancement of the aperture or antenna length, and that enhancement we are doing synthetically. That's why the name is synthetic aperture radar. So they are basically giving more or high spatial resolution images. Okay, so these are the imaging radar, RAR, and the SAR. And non-imaging categories are the altimeters and the scatterometers. So scatterometer data is also very useful. People are using for the ocean applications. So suppose sea surface height, sea salinity, or sea roughness, all those things we can very easily investigate with the help of the scatterometer data sets. Altimeter data sets, the water surface information you can directly investigate, just like the water level in the rivers or the seas, or in the cities, especially in the water logging situations. So the water level, if you want to monitor, so that is called the altimeters are very much useful for such kind of the investigation. So hydrology studies you can do using the altimeters also. And if you have the very precise DM also, then you can calculate the depth of the water also. So that is called the bathymetry. So bathymetry applications can be done easily with the help of the altimeter data sets. Ocean applications with the help of the scatterometers. Land surface applications, people are also starting using the scatterometer data set. Radar, synthetic, and the RAR using for the land applications or the deformation applications. Radiometers, again, enhancing the thermal components basically, because these are working on the emitted radiation. So emissivity is somehow related with the physical temperature of the bodies, because according to the Kirchhoff's law, any body which is having temperature greater than 0 degree Kelvin, they can emit the radiation. It means earth surface is already more than 0 degree Kelvin. This is around 25 degrees Celsius, or more than that, somewhere less than that, but still they are able to emit the radiation. So those radiations are indicating the temperature information of the earth surface. So somewhere if you want to analyze the drought conditions in the country, or vegetation health, suppose somewhere more temperature is there and soil moisture is less, so the vegetation health will also get reduced, or any other such types of the things are happening. So in all the fields you can use radiometers data sets. And as I mentioned, both the techniques have their advantages and the disadvantages. So what happens, if you want to analyze them very critically, then you can combine both the data sets. And still, the beauty of this sensing is basically in the active remote sensing, and all these microwave systems are using the longer wavelength. So they are having very, very less effect of the rain or the cloud or the fog or the smoke or the any kind of the dust which is there in the lower atmosphere. So these signals are not very much affected by those types of the disturbances, or you can say these signals can penetrate those types of the disturbances very easily. So for that purpose, these systems, these signals can reach to the earth surface in any situation. Or suppose very rain is happening, these signals can cross the atmosphere and they can reach to the earth surface. It means they can carry the information of the earth surface during the rainy season also, during fog also, during cloudy situation also. And in optical cases, suppose clouds are there, you cannot have the images. You cannot acquire the images. Only the cloud surface will come into the optical images. So point is, these microwave systems having many advantages over the optical and the thermal microwave remote sensing products. And second thing is, if you particularly focusing on the active microwave remote sensing, it means they have their own source of energy. Own source of energy means they are not depending on the sun illumination. Means they can work in the night time also, in the daytime also. So it is independent of the sun. Means if somebody wants to acquire the data set in the night time, they can acquire from the active microwave remote sensing systems. And somebody wants to acquire in the rainy season, they can acquire. They can they want to acquire the data in the winter season, the fog situation, they can acquire. So in all the situations, these are having basically some plus points over the optical remote sensing data sets. And this is happening because, see, the active devices, or you can say the active microwave remote sensing, is only possible for the microwave portion, not for the optical portion. Suppose this active sensing means system itself is generating that radiation. But if you are generating the optical sensing or optical radiation, so optical, if you compare the optical and the microwave portion, it means microwave portion wavelength is more than the optical length, optical wavelength. Okay. So as the wavelength is less, and if you know the fundamental rule of the photon energy, E equal to h nu, Planck's formula, E equal to h nu. E is the energy of the photon, h is the Planck's constant, nu is the frequency. Okay, it means high frequency, high energy. If nu is high, it means energy is high. Nu is less, energy is less. So you can say the frequency of the microwave portion is less compared to the optical portion. So you can say if nu is less, it means E is less. It means less energy is required to generate those types of the photons. Means if a small fuel is there with your satellite, then you can generate a large amount of microwave radiation. But with that constant fuel, you cannot generate that much optical radiation, because optical frequency is very high compared to microwave. So E equal to h nu. H is constant, nu is more in case of optical. So frequency is more. It means high energy photons you have to generate if you are interested in the optical radiation generation. So if you are, or in other words, we can say if you are generating the optical radiation, then your fuel will finish quickly. It means your satellite will end in less time, or life of the satellite will be very less. That's what nobody is generating optical radiation with the satellite itself, or you can say the optical systems or active optical systems are not available. Okay, so point is, this active nature of the microwave, active nature of the remote sensing is only available in the microwave portion. That's what the people are using. And lot of advantages of microwave systems is there, like uh, some disaster is happening in our country, and during the disasters, the atmospheric conditions are not favorable in nature. Like landslide is happening, some heavy rainfall is there. If cloud burst is happening, it means some heavy rain is there, or cloud is there, or let us say some other disaster, or let us say tsunami is happening, then again cloudy cloud or atmospheric conditions are not okay. Tsunami is happening, that atmospheric conditions are not good. So in these difficult atmospheric conditions, active sensing can work because of the penetration capabilities, but these capabilities are not there with the optical sensors, and hence we can say optical sensors cannot work during these emergency situations also, especially in the disaster situations. So you can say microwave portions are very much useful for handling the emergency situations in the country, or you can say the disaster situations in the country. So that is another advantage of the radars, or you can say the microwave remote sensing systems. Okay, so there are a number of applications. Now here you can say SAR systems are of the two types, basically operational SAR two types, like monostatic SAR and the bistatic SAR. But concept of multi-static SAR is also there, but theoretically it is possible, but practically no one is having the multi-static SAR system. SAR means synthetic aperture radar. Okay, monostatic means they have only single antenna, and the same antenna can be used for the transmission of the signals as well as the reception of the signals. So single antenna, both the things cannot do simultaneously. So what if they are happening? Basically, for some instance the antenna is transmitting the signal, then next instance it is not transmitting, it is only receiving the signals. So alternatively it is basically transmitting the signals and the receiving the signals. So this particular mode of SAR is called the monostatic SAR. Mono means single, single static SAR. Okay, and bistatic SAR, it means it is having basically the two transmitters, or you can say two antennas. So one antenna is used for the transmission purpose, another antenna is used for the reception purpose. Okay, so one antenna is continuously is transmitting the signals, another one is continuously receiving the signals. So that mode is called the bistatic SAR. But yes, that may be possible. Suppose first antenna is transmitting for, let us say, 1 hour or 2 hour, and second antenna is receiving, and after 1 hour the functioning is changed. The receiving antenna is now transmitting, and the transmitting antenna is now receiving. So depending upon which area we are trying to cover, so alternatively they can be used. So that concept is called the bistatic synthetic aperture radar systems. In multi-static, there may be more than one transmitting antenna or more than one receiving antenna also. So they can be used for alternatively, but main thing is more number of antennas are there for reception as well as the transmission purpose. But currently there is no multi-static synthetic aperture radar available, either in the neither in the airborne or nor in the spaceborne platforms, but they are actually under experiment. So people are trying to develop it, but theoretically it is possible, practically not operational. So in the radar systems, basically there are three things very important. In fact, here I have noted down the 5 things. One is the transmitter, another one is the receiver. So transmitter transmit the signals, receivers receive the signals. Okay, another one is called the antenna, which is basically transmitting and reception of the radar signal is happening. That may be single or dual. And another one is called the duplexer. Duplexer means is a kind of device, or you can say a switching device, which basically change the action of the antenna. Means, as I mentioned in monostatic SAR, for momentarily it is using for transmitting the signals, then in the next instant it is used for the reception of the signals. So the action of the antenna from transmission to the reception, this action can be switched by a device, and that device is called the duplexer. Okay, and more importantly the recording device, because whatever the energy is stored, that should be recorded properly, and the recorded in the form of the images. So recorder or recording device is also there as a part of the microwave systems. So this is the functioning like this: a transmitter or the receiver in the single antenna, and signal is going. This is the target. From there it is back scattered. So some scattering is going this side, some scattering is going this side, and some scattering is coming back. So this one is called the back scattering. This is called only scattering. Okay. So this one is called basically backward scattering. Back scattering. This is called the back scattering. Back scattering, and that is called the backward scattering. I'm scattering is going this side. That is called the forward scattering. So scattering, you can understand, three types of the scattering are there, but broadly there are two types: forward scattering and the backward scattering. And in the backward scattering, but specialized one is called the back scattering. Okay. So here you can just understand, suppose here I'm drawing a perpendicular from here to here. So if these rays are going this side means the signal was coming from this side to this side, and after scattering it is going towards this side. So this is going in the forward direction. So this is going in the forward direction. It means that is called the forward scattering. Okay. So here you can say if it is going this side, so this is basically 0°. So in terms of angle of direction, we can classify this is 0°, or from up to here. As I mentioned, the perpendicular if you are drawing here. So the scattered signal from 0° to 90° and 0° to minus 90°. So you can say minus 90 to plus 90° from the propagation direction. Whatever the radiation is going outward, that is called the forward scattering. And on the other side, here you can say if this is the perpendicular, so from this 90° to 180°, or here again minus 90° to minus 180°, or you can say simply from 90° to 270°. So whatever radiation is going in this direction, that is called the backward scattering. So you can say from 0 to 90 or 0 to minus 90, in this direction whatever scattering is happening, that is forward scattering. And just opposite of this, from 90 to 270°, backward scattering. And in the backward scattering itself, the scattering can happen this direction also, this direction also, this direction also, but that scattering is not moving towards the receiver or the antenna, but only this specialized signal, means this one which is at 0°, or sorry 180°, because the signal is going in this direction and now just taking U-turn. So again the direction means the angle between the transmitted signal and the reception signal is now 180°. This is this one, now this is this one, it means 180°. So whatever the 180° signal is there, that can reach to the receiver. So that is called the back scattering. Okay. So you can say out of the backward scattering is happening from here to here, but back scattering is only at 180°. So back scattering is basically used for the radar system. So everywhere in the books or in any kind of literature, especially in the radar systems, you will see the term back scattering, not the backward scattering. Somewhere they can use the backward scattering, but that is means all backward scattering is not used. Only the back scattering, which is at 180°, that is used for the this type of the devices. So now this is the working principle of the SAR, that is called the synthetic aperture radar. So here you can see this is radar, especially the space-borne radar, and this is the Earth surface. Now here you can see two targets are put it, target A and target B, and the signal is transmitted from here. So here you can see the signal is just like a beam is there. So beam is covering, just like a torch. So the coverage of the torch is just like this. As the distance increases, so it is, let us say, moving towards this side, and this is toward this side. So overall coverage of this radar signal, if you see on the Earth surface, so it is from here to here. So you can say very large coverage on the Earth surface is there. So, and whatever the signal it is sending, so there are two types of the signals. One is the continuous wave it is sending, then it is called the continuous wave radar. And there is another type of the radar that is called the pulse radar. It means it is sending the pulses. Pulses means a bunch of cycles of the signal. Suppose in this bunch only 5 cycles are there. It means sensor is sending 5 cycles, then it is stopping for some time, then after that time again it is sending a bunch of 5 cycles, and the bunch of 5 cycle is called the pulse. And total length from this to this is called the pulse length. Okay, and this is called the pulse started, pulse ended, or you can say from the here to here it is called the pulse length. So if the radar is using no sending the signals in the form of the pulses, then it is called the pulse radar. But in remote sensing, generally we are using the pulse radar. As I mentioned, if we, in case of the monostatic SAR, the antenna is used for both the purposes, means for the transmission of the signal as well as for the reception of the signal. It means a sensor is sending one pulse, then some gap is there. In that gap, it is receiving the signal. Then after that gap, again it is sending the signal. Signal means that pulse. Then again it stopped. During the stop period, it is receiving. Then again it is transmitting, the pulse. Then again it is stopping. So during that stop period, again it is receiving the signals. So that way it is working, or acting as a receiver as well as the transmitter. So you can say the pulse radar is suitable for the interferometer. Oh, sorry, for the microwave remote sensing. Okay, so both the purposes are solved. Second thing is, another advantage of the pulse radar is, suppose we are sending continuous signals. It means this is continuous wave radar. It means signal is or the device is continuously operated. Continuously operated means it is taking more energy, means continuously you have to generate those pulses or signals. If you are generating continuous signals, it means more input energy is required or more fuel is required. If you are generating the signal in the form of the pulses, it means you are generating less number of photons. It means less input energy is required or less fuel is required. So the pulse radar have uh, number of advantages over the continuous radars, especially in the remote sensing. This concept is not true everywhere. Suppose in defense applications we are using uh, the radars. So there generally we are using the continuous wave radars, because there we want continuous monitoring. So there we are rarely using pulse radars. But here, for the economic purpose or for the technical limitations, we are using the pulse radars. Okay, so now the pulses are basically moving from the sensor side to the surface. So here you can see these pulses are moving just like spherical wave fronts. So like this it is moving. So what is happening? It will interact with this target first. When it is interacting with this target, so it means the signal will start back scatter from this target. So you can see the signal has started in the backward direction, but from this portion of this pulse, the pulse is still going on forward in the forward direction. Then it is basically reaching to the another target and then scattered from this. So from this target, it is basically reflected back. So now you can see the back scatter process from this target is started earlier than this target. So what is happening? This back scatter signal from here will reach first to the sensor, and this signal or this pulse will reach to the later to the sensor. So sensor is very easily to able to differentiate both the targets because of this differentiation in time. Means the same way you can just imagine if targets these type of the targets are at different distance, here, like that. It means from each targets, whatever the backscatter energy is there, that will reach to the sensor at different times, and the sensor can capture those differentiated information, or you can say the information of each and every target. It means the sensor can see all targets very easily. So that is the beauty in the sense, because that is called, this backscatter signal is also called the backscatter echo. So suppose this echo is reaching, simultaneously from all the targets, then sensor cannot differentiate all these echoes. It means sensor will be confused. Sensor cannot differentiate, okay, this energy is coming from which type of the target. Means sensor cannot differentiate the targets, but sensor can differentiate if the echo is coming from different targets at different times. Just like, we are sitting in a multi-story building and we are speaking something, so that voice is, or let's suppose we have mic and we are speaking, so that sound is going and reflecting from different walls. And since it is multi-story building, so the reflected, or you can say the echo from different walls is coming differently. That's why it is, sound like this. You are speaking once, but the echo is coming again and again for, some time. It means that echo is coming from different walls, and those walls are different distances from you. That's why you're observing different echoes for longer time. So same type of the situation is happening here. Means that echo of the microwave signal from different targets is reaching to the sensor, and sensor is capable now to differentiate all these targets according to the distance. So target now can tell, okay, this target is at this much distance, this target is at this much distance. Okay, so means this radar job is detection and ranging. So now target, this radar can tell, okay, this object is at this much distance, means detection and ranging both is happening now. So, and this target is at this much distance. Okay, so now easily we can, the radar can differentiate all the target, but the fashion in which we are looking this sensor, this is called the side looking. You see, generally the sensor is neither looking, means directly it is moving, looking towards the surface, but this looking is basically called the side looking. You can say this is the right looking, but left looking is also possible. Means neither looking radars we are not using for the remote sensing purpose, just because of that nature of the backscatter echo. For example, see, if we are putting in the northern looking, suppose the sensor is, looking towards this side, that is called the northern looking. So here the targets are there. So backscatter echo from all the targets will reach at the same time to the sensor, and sensor cannot differentiate those echoes. It means sensor cannot tell, okay, this target is at this much distance, or no, this signal is behaving like this. So you can say very bad quality of the images we will receive. If bad quality images are received, it means the purpose is not solved. But if the sensor is operated in the side looking mode, then all the targets can be differentiated very easily. That is the beauty. And if you see in the subsequent slides, we can see what happens. Since this radar is moving towards this side, so this distance is called the range. This is called the ground range, means the distance between here to here, it is called the range, ground range. Okay, and the distance from here to here, it is called the slant range, and distance from here to here, again it is called the slant range, and distance from here in intermediate situation is also called the slant range. So you can say slant range is varying, but this one, the lowest one slant range, is called the near range or near slant range, and this is called the far slant range. So in between far and near, so many type of the slant ranges are there. Okay, similarly for the ground range, this is called the near ground range, this is called the far ground range. And since the satellite itself is moving, so you can say this coverage is continuously traced, let us say this side, and the direction along the movement of the sensor, that is called the azimuth direction. So these sensors are having two types of the resolution. Resolution means the capability to distinguish the objects according to their distances. Okay, so now the distance is along this direction, and distance is also along this azimuth direction. So these radar images are governed by two types of the resolutions. One is called the range resolution, or capability of the sensor to distinguish the target along this direction. That is called the range direction, or capability of the sensor to distinguish the targets along this direction. That is called the azimuth direction. So SAR images are having two types of the resolution. One is called the range resolution. Another one is called the azimuth resolution. Okay. So the resolution, if you talk, then we will see in tomorrow. I will show you the capabilities of the sensors along the range direction and along the azimuth direction. So see, azimuth direction is here also, here also, here also, everywhere azimuth, because the entire swath, this is basically called the swath also. This entire swath is traced along the azimuth direction. So everywhere we will have the azimuth resolution, and everywhere we will have the range resolution. So if you see, this is the near range, but the range resolution this side is coarse, but the range resolution at the far range is better, or you can say high resolution. So you can say high resolution images we will get at the far range, and coarse resolution images we are getting in the near range. Means the distance is less, but the resolution is bad. Range is high, but resolution is bad and good. It means these are the special quality of the synthetic aperture radars. Means as the distance increases, they can see the targets in a better way. This is just because of the separation of these pulses, because these pulses are coming little later, so that the radar is comfortable in distinguishing the responses from these targets. So that way, basically, the resolution capability at far range is better than near range. So these things we will discuss tomorrow again. And this bit is basically called the beam width. So this beam width is again along the range direction as well as along the azimuth direction. Okay. So we will see the relationship between how much beam width we should keep, and what should be the antenna length, and which types of the radiation can give better resolutions. So the resolution is basically depending upon different types of the satellite parameters, or you can say the antenna parameters, like the beam width, antenna length, and then directivity. Directivity means left, right, and if it is left, then how much left, that is also governed by different angles, angle of incidence, look angle, depression angle, so many angles are there. So how that spatial resolutions vary according to the satellite parameters, and also according to the different properties of the targets. Okay, so that we will see. So now I will end this lecture today here, and now if you have any questions, then we can discuss, and later other things we will discuss tomorrow.